everybody. Welcome back to Markov Processes. I hope you recovered from the exam. I think it was rough. It's actually not going as bad as I thought, but I'm still grading it. But I do think there's going to be a curve, so don't be too stressed. Yeah, so currently no homework. Grad student take-home exam came out today. This one's only 2 questions. It had 3, but because I was so late with it, I decided to make it only 2. You'll have essentially to the end of the semester. So I thought we'd kind of start with a simulation break today. But to do that, I need to talk about just a couple of things first. The concept that I wanted to talk about first is that of detailed balance or reversibility of a Markov chain, or it also is called reversibility. This is a property a Markov chain could have, but it doesn't have to have. But when it does, nice things happen. So first, I want to go back to the very beginning of the semester when we had discrete time and discrete space. Back then, we had transition probabilities. We called them P sub ij. There was no need to put an of t. And so suppose we have a Markov chain with transition probabilities Pij. And then suppose we have a probability distribution on the state space. So let me be clear about that. It is a Markov chain sort of on a state space S with these transition probabilities. So suppose we have a vector of probabilities or a probability distribution, pi, that also lives on S. Now I'm using a pi, but I'm not saying it's stationary or a limiting distribution. So using a pi seems like a bad choice of words, or symbols, but give me a minute. Okay, so if this pi satisfies the following equation, pi I Pij equals pi j Pji for all I and j in the state space, then we say that we say the chain has detailed balance with respect to the distribution. This is not something that's going to hold for every Markov chain, but it has detailed balance or reversibility with respect to this distribution pi. With respect to pi. But a really nice side effect here or result of this is, check this out. If this holds, so I'm going to put pi I Pij equals pi j Pji. I'm going to sum both sides of this over all I in the state space. So there's the left side and there's the right side. And on the right side, this sum is with respect to I, so the pi j can be pulled out. And I've got the sum with respect to I of Pji, and that is summing across the jth row of P. So that sum is 1. So we get pi j. And now you can see why I called the distribution, I named it with a pi, because this equals this is the stationary equation. So let me put that all together. If pi I Pij is equal to pi j Pji for all I and j in the state space, then pi is stationary for the chain. And one more time, this is called the detailed balance or reversibility condition. For the chain, meaning the chain running according to the given Pij's. So that's pretty cool. And it also might give you some hints about finding a stationary distribution when your transition probabilities are symmetric. Like if Pij is equal to Pji, then you can get this satisfied with a constant pi, although that would not work if you have an infinite state space because you wouldn't be able to normalize it. But it's this fact, this reversibility and detailed balance, which goes into a lot of Markov chain Monte Carlo algorithms, the first of which we're going to talk about today. And that is simulation from a distribution by creating a Markov chain. Where there is no Markov chain and you're not interested in a Markov chain, we're going to have a target PDF and we're going to create a Markov chain that has this as that target as its stationary distribution, which is pretty cool. So Before doing that, let's go back to our discrete state continuous time Markov chain. So continuous time Markov chain on a discrete state space S. So when we started talking about this, we no longer have the PIJs. We have PIJ of T, and that's kind of hard to deal with because T can be quite variable and the probabilities are changing as T is changing. So this is where we use the generator matrix, right? We've got a generator matrix that we call Q, and it's filled with QIJs, and QIJ is the rate of transition from I to J, in some instant of time. And reversibility or detailed balance now looks like this. If we have a distribution pi on the same state space where pi I qij is equal to pi j qji, then I claim it is stationary. And this has to hold for everything in the state space. Let me move this down a little bit and say that this is not necessarily going to hold for your stationary distribution. But if a distribution pi living on the state space S satisfies this condition, then pi is stationary for the chain. And we're going to show this in the exact same way. We're going to sum both sides over I. So check it out. If you assume this holds and you sum both sides over I, then you get the sum over I of pi I qij equals the sum over I of pi j qji. And because that second sum is over I, we can pull the pi j out. And now we find ourselves summing across the jth row of Q, but that sum is going to be 0. And on the left here, I've got the jth entry of the row vector of pi's times Q. And on the right, I have 0. So what we have is the jth entry of pi Q is going to equal 0 for all j. In other words, pi Q is the 0 vector. And so we have continuous time Markov chain T1 for theorem 1 tells us that pi is stationary for this chain. How often does this occur? Not that often, but it does if you force it to occur, which is usually how Markov chain Monte Carlo algorithms go. So when you hear about a Monte Carlo algorithm, you are computing something using randomness. And when you put Markov chain in front of it, you have what is known as an MC-MC algorithm. And this is where you're trying to sample from a distribution, just like we've done all along, but maybe you couldn't get accept reject to work. And maybe you went through several others that you couldn't get to work. So you create a Markov chain that converges to your distribution. And this idea of reversibility or detailed balance is really the way to get some of these recipes. By recipe, I mean you're creating like transition probabilities. So before we can talk about the famed Metropolis Hastings algorithm, that's what we're going to do today. I do need to talk about some notation because this is going to be our first example of a continuous state space and discrete time. And it's just for this algorithm. We're going to go back to birth and death processes and back to continuous time in a discrete state space. So the Metropolis Hastings algorithm that's coming up, you could use it for a discrete state space, but I think there's better things to do. And I just want to describe this in the continuous state space and also get some more notation out to you. So the target density, meaning the thing you want to sample values from, might be some f of x, and x could be high dimensional. But because the idea is that we're going to create a Markov chain that converges to it, I'm going to call the target pi of x, which is what you're going to see if you ever look up anything having to do with the Metropolis Hastings algorithm. And I know I haven't written the title down yet. If you're not catching those words, I'm going to write that soon. And so I'm assuming it's continuous. This is not a requirement for the algorithm, but almost always how the algorithm is used. And the X, again, can be high dimensional. So in order to create this Markov chain, we need to know what it means to have a continuous state space. So these, I can certainly go into negative values on the state space. I just always draw my axes like this. So we're going to talk about discrete time. And at any time n, if your chain is at a point x, then at time n plus 1, you simulate a value, you draw a value for the chain from some continuous distribution that depends on x, or maybe doesn't depend on x. So let me just get a line here. For example, we haven't talked about the normal distribution yet in here, and we're not going to talk about it too much, but if you have a normal distribution sitting over here, and yeah, this goes negative, centered at x, that is something that could drive the chain forward. Given you're at x, you can draw a value y from the normal distribution, and then you call that your new x, and then you can draw a value y from the normal distribution. And I'll tell you how to do that in a moment. But we have a transition density, a PDF. We no longer have Pij because we don't have a discrete state space. We do have discrete time, so we don't have to worry about an of t, but we move to a Px comma y with that more functional notation. And this is a PDF in y, and x is fixed and considered to be a parameter of this PDF. So in the example I've drawn here, in this example, my Pxy is the normal distribution PDF, maybe with some variance, which would be a given parameter here. And then e to the minus 1 over 2 sigma squared, y. So don't write this, but usually it looks like this, y minus mu squared. But I'm going to make the mean the given x. So that is the PDF for this curve right here, where sigma squared is just a parameter that controls how flattened or spiky it is spread out. It's a variance parameter. And don't be too concerned if you're not up on the normal distribution. It's just an example. And so for any PDF, let me go back up to the right here. If it's going to be a PDF in y, then we need two things. We need it to be non-negative. And we also need, if we integrate it over the state space S, minus infinity to infinity, 0 to infinity, 0 to 1, whatever that is, if we integrate it with respect to y, we're going to get 1. This transition density that I've written here is actually kind of special because it's symmetric in x and y, and I'll talk about why that might be useful later. But continuous state space. Our new notation for the stationary distribution is a pi of x. Oh, well, I haven't defined that yet. But our notation for a transition density is a PDF called Px comma y, and it's a PDF in y. Okay, so now let me define stationarity. Stationary distribution is going to be a pi. It's going to be a continuous distribution. So before, and I mean discrete time and discrete state space, the stationary equation was pi j is the sum over I of pi I Pij. And then when we went to continuous time, we had a Pij of t. And I just write that so you can sort of see the analog here. We are going to get, so this is something that is you moved from I to j and you considered all the possible starting points. I'm going to rewrite this. This is what it looks like for the continuous state space. Pi of y, and then because it's a continuous state space, we end up integrating over whatever the whole space is. I hope that's not freaking anyone out to put a set under the integral. I know it's not for most of you, but integrate over the space you're working in. Pi x, p x y, and then if you look up at the sum, we we're summing over the first index in the P, and we are here as well. So this is going to be with respect to X. This is the stationary equation. Okay, so in this discrete time case with a continuous state space, we do have the idea of detailed balance or reversibility. I'm going to call it reversibility this time. Same thing as detailed balance. If you are given a transition probabilities Px, y, and you can find a P, so let's say, let me write that. You're given Px, y, if you can find a PDF pi of x on the space, whatever space you're working on, then the reversibility or detailed balance condition now looks like this. Pi of x, p x y equals pi of y, p y x. And if you can find such a PDF with respect to the given transition density, then you have found a stationary distribution, because if you take this and you integrate both sides with respect to x, what I have right now, what I've written, is actually the right-hand side of my stationary equation. And when you put this on the other side, integrating with respect to x, you can pull the y out, or the pi y. And then you have an integral p y x dx. And this is integrating a PDF. The second argument is the argument that it's a PDF. And so this integral is 1. Before I had pxy, you had to integrate with respect to y. But you can see you get the stationary equation to hold as a result of having this reversibility or detailed balance condition. Again, doesn't happen that often in a natural Markov chain, but it's great news for simulators who want to make up algorithms. I didn't really plan on talking about the normal distribution, but just because I mentioned simulating from it, I'm just going to really briefly, there's many things you can do. The maybe the most common one is the Box-Muller transformation. You're going to need MathStat to fully appreciate this, but for simulating from the standard normal distribution with mean 0 and variance 1, if you don't know what I'm talking about, don't worry about it. This is just for fun. And here's a cool result. So if you take a U1 and a U2, and they are IID uniform 0, 1, and then if you compute an x1, which I'm going to define to be the square root of -2 log U1 cosine 2 pi U1, and an x2 is going to be the same thing, but with a sign in it. If you've taken mathematical statistics, what you're seeing is a transformation from 2 random variables to 2 others. And you can write down the joint PDF for the 2 U's because they're uniform. You get to multiply the individual PDFs. And you can use the Jacobian method to find the joint PDF for the X's. And you will see, but it's just outside the scope of this course, that X1 and X2 are IID. They're independent. They look so closely related, right? But they're IID normal 0, 1. So this is, if you've had it, a Jacobian problem from MathStat. If you wanted to simulate from a normal distribution with a different mean and different variance, you just need to take these values and multiply to rescale them and add or subtract something to recenter them. And be happy to talk to you more about that. Want to come on by my office hour? But I want to get back to the algorithm. Yeah, so what is our algorithm here? The Metropolis Hastings algorithm. Check this out. This was first developed by Metropolis in the 1950s in statistical physics, like mechanics models. I'll come back to that. But and then Hastings came in the 70s and generalized it a bit. For the longest time, it was called the Hastings Metropolis algorithm, but in the late 90s, there was like this push to name it the other way because Metropolis was first. And so now everyone says Metropolis Hastings, but if you're reading something old, it might say Hastings Metropolis. Okay, so I just want to start out to be clear. There is no Markov chain in sight. You are not working with a Markov chain here. We're going to create one though. And you have a target density or PDF. We could call f of x, but I'm going to call it pi of x. X can be high dimensional. It could be really high dimensional. I've used this algorithm on 30,000 dimensional vectors. Okay, so before you run the algorithm, you have some setup like we did with accept reject. We had to find that bounding function. And the setup here is we need to choose a so-called candidate transition density or PDF. This is not going to be the P of the problem. We're trying to build one. So it's usually called Q of X and Y. Sometimes people will call it Q of Y given X, like where do you go given you're at X? I'm not going to do that for a bunch of reasons. But this is going to be a proposal. And what is going to happen is if at some time n you're at an X, at time n plus 1, we're going to simulate a Y from this PDF. And then we're going to choose to either accept a move or not. And if you don't accept, you don't really stay where you are. It's not exactly accept or reject. You keep on moving forward. So you stay flat. There's going to be two options when we propose from that density. So everybody's okay. I'm ready to describe the algorithm. And yeah, I mean, we can talk about choices for this, but I only have good advice for a particular class of those PDFs. But let's write down the algorithm. So here goes. Oh, and I didn't write it here. I keep saying it, so let me give it some nice bright color. We are going to create a Markov chain that has stationary distribution pi. This is an MCMC algorithm. MCMC stands for Markov chain Monte Carlo. So let's do it. The Metropolis Hastings algorithm, we're going to start at an arbitrary point. I'm going to call it x0. Again, this could be a vector, could even be a matrix. And so I don't think it's worth putting an n and n plus 1 in the algorithm. So let me just say like at any time n, suppose the chain is at some value. You could call it xn, but I'm just going to say suppose we're at x. Just like my pictures, at any time n, we're at some x. So suppose the chain that we're forming is at state x. Here are the steps. The number 1, you propose or you draw, you simulate. You simulate a y from the candidate transition density qxy. And then you accept a move from x to y with the following probability, WP, with probability. This is always called alpha xy, because alpha is like an A for accept. And it is defined to be the minimum of 1 and then a ratio pi y q yx over pi x q xy. And if we didn't just have that reversibility conversation, I think you would be like, what? What just happened? Like why? But it's reversibility that's driving this algorithm, and it's kind of really manufactured. And let me just say that if you don't accept the move, so by the way, an accept, that means you simulate a uniform 0, 1. And if your uniform 0, 1 is less than or equal to this, then you accept the move. Yeah, and so otherwise, you stay flat, but you move forward in time, but you stay flat at x. So if I really wanted to write this algorithmically, I would say something like xn plus 1 is xn if this happens, or it's a new value drawn from Q. But I don't think anything was lost in this. I don't know. Let me know. It's too confusing. Okay. And I want to talk about why this converges to the right thing, but how to get your draws from pi. State space could be negative, but you're going to start at kind of an arbitrarily chosen x0, and you're going to move forward in time. At each point, you're going to be proposing a value, proposing a value, proposing a value. And you're going to have like a y associated with each time step, and also grab a uniform associated with each time step to check whether or not you're going to accept. So maybe this could go there, and it could go here, and maybe it does not accept and goes right here. And then it has this proposal, and maybe it accepts that one, so it kind of moves. Maybe it accepts this one, but with the next proposal, it doesn't, so it stays flat. So you get a bunch of like proposals. You either move to it or you stay flat. And you want to go for a long time. And what I'm going to show you today, it's actually a ridiculously short time to get our results. But the idea is at the end, you should see whatever the target distribution was. This is like a pi of x graphed sideways. The answer to what is a long time is really difficult to answer in general. But as I was saying before, there's a certain class of candidate transition densities for which we know some things, but this is going to be really problem specific. And so before the end of this semester, I do want to show you a diagnostic for on the fly assessing of convergence. It's if you've ever seen this stuff, it's called, don't write this down, we're not talking about today, but it's called Gelman and Rubin's R statistic. And it's a pretty neat thing that can apply to a lot of problems. Okay, so why does this work? So I'm done describing the algorithm. The transition density, or PDF, for this chain is going to be some pxy, and it's not the q because we have the accept or do not accept step. So pxy, to go up, I want you to think that this is not a probability, right? Because this is a continuous PDF in y, but we can often think about it just to talk about it. This is kind of like the probability you go to y, given you're started at x. And this is the probability you propose the y starting from x, multiplied by the probability you accept the move from x to y. That acceptance is independent because the uniform you draw is supposed to be independent. So at each state and time, you are proposing a value, so you need something to generate that, and then another uniform to see whether you accept it or not. And there actually is you can stay flat, right? So you don't have to be concerned about this at all for running the algorithm, but we often write px x in brackets. The brackets are indicating that, something different is going on here. This is not exactly a PDF. There is some positive probability of going there. Like starting from x, what is the probability you are still at x? I'm going to not use it, I guess, but this is actually a probability and not a PDF. And so this is going to be, you were at X, you proposed a Y, you failed to accept it. So I'm going to multiply by 1 minus the acceptance probability. And then I'm going to integrate over all the Ys you could have proposed. So if you want to show that this is going to give you the right thing, and you try the stationary equation, so if you want to show that pi of y is the integral of pi of x, p x y dy, and you want to know if that holds, and then you plug in the q of x, alpha of x, and then you plug in the definition of alpha, which is a minimum thing, and then you split it up into a couple of integrals, one side which, where the minimum is 1, and the other side where the minimum is not 1, but formed by the ratio. This is a mess, and yeah, I don't think you'll get anywhere, actually, honestly. It's hard to take this definition of the transition probability and show that you have something stationary. But it's not if we have reversibility. And that's exactly why Metropolis and Hastings define that ratio as they did. So I'm not going to try the integral approach. So note that I don't know how this goes. Pi reversible with respect to p, or p reversible with respect to pi. I suppose either would be okay, but note that pi of x is reversible or has detailed balance with respect to that trend, with respect to the transition density. And that whole min thing is how we're going to show this. And then we don't have to bother showing stationarity through the integral. Okay, so I'm just going to look at this case. It's clearly reversible when you have x, like pi x pxx is equal to pi x pxx. But I made quotes, air quotes, for clearly, because you have to kind of think about what this means. It's a little mixed distribution. So I'm just going to look at the kind of more interesting case. Pi of x, pxy. We want to show that this is pi of y, pyx. So what is the definition of pxy? It is qxy, alpha xy. And what is the definition of alpha? This was formed by a minimum of 1 pi y q yx over pi x qxy. And this could give you your own ideas, this reversibility property about how you might make your own algorithms. But yeah, I'm going to multiply this in. So these things are all non-negative, right? If you were multiplying just to check, like 3 times the minimum of 1 and 5, that's the same thing as the minimum of 3 and 15. Like, you can multiply that in, and that's exactly what I'm going to do. So I get the minimum of pi of x q x y, and then in the second part, it cancels with the denominator. So we have the numerator pi of y q y x. And now you just pull out the other one. So I'm going to pull out pi of y q y x, and that's going to leave me with a minimum of pi x q x y over pi y q y x and 1. And yeah, the minimum can be in either direction, but that's the alpha, but x and y have been switched. So it's actually alpha y comma x. And the q times the alpha is the p, the transition probability starting at y that you're going to choose x. So look where we started in the upper left corner, and where we are, we have reversibility or detailed balance. Let's go to, actually, yeah, I have a simulation to show you, but I want to say a couple of things first. 3 things to be exact. Here are my things. One is to note that pi of x, or pi, not put it of x, only appears in this algorithm through a ratio. And that means that, here it is. And that means that you could be missing constants of proportionality and still run this algorithm. And that is a very distinct probability in a lot of cases. If you know about Bayesian statistics, you definitely see this a lot. And there are some models in statistical mechanics where you have computed, like you have huge, like the Ising model. I didn't really mean to depart, but it's a bunch of sites on a lattice where you have things called spins, which are little like magnet vectors that point up or down. And there is a Hamiltonian that goes with this that sort of governs how they interact and whether they want to be aligned or not. And so, if you can see me in the box, but if the parameters are such that they want to be aligned, you've got these little magnet vectors that are like, and then it flips. And then now maybe it's out of alignment with the other one. And so they all flip. And there's a particular distribution of interest here. And if you have, it's supposed to be infinite, but if you have an n by n grid, like I've simulated this for a 500 by 500 grid, that means you'd have 2 to the 500 by 500 states. It's a discrete state space, but a lot of states. And the physics model gives you the PDF, but not the constant. You need to sum over all of these to get the constant, which is terrible. So there's lots of times where you only have that pi is proportional to something, and that's okay because it only appears in a ratio. Actually, I might talk about this model, but not right now. So you can be missing constants of proportionality. A second thing to note is, I should have called it notes, right? But note that our normal candidate that we wrote down before, it was qxy equals 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared y minus x squared. So we're going to draw y from a normal distribution centered at x. This is symmetric. And, you can switch the x and y, i.e. qxy is the same thing as qyx. And if that's the case, the q's are going to completely drop out of the ratio. And so the acceptance ratio is going to be simpler looking. It's going to be the minimum of 1 and pi y over pi x. And this was Metropolis's original algorithm. It was Hastings that came in 20 years later and generalized it a bit. It's hard to choose candidates. Just like the accept, well, you certainly want them on the same space. And just like the accept reject algorithm, you would kind of like them to be, well, you want them to be pushing you towards pi. And that's what it's doing at every step. You propose a value from Q and you maybe accept it or not, and that's pushing you towards pi. You want the tail of your candidate to be fatter. You want more probability out at the ends. Yeah, there's a lot. Wait, let me just finish my note because I want to show you a simulation. So you can use a so-called independent candidate. This is the easiest thing to do because you don't have to think that much about it. By this, I mean that your qxy is just a q of y. So at any point, you're proposing something independent of where you are. This is the easiest thing to implement. And also, this is the class of densities for which we know a lot of things about the convergence rate of the Metropolis-Hastings algorithm. Because at each point, you are proposing a Q and you're accepting it or not accepting it. And so there's a geometric thing behind the scenes here. And we know a lot about convergence of this sort of thing. But I think this is the easiest way to get started. Just propose something independent of where you are. So now, yeah, let me go to my you know what? Before I go to my target, I want to say some things that you're going to see in the slides. So I picked an example. I was trying to get something weird and multimodal. And so the target is pi of x is proportional to the absolute value of the sine of x times the cosine of x, e to the minus x. So this kind of alpha thing is proportional to, is proportional to. And I originally was going to do this on all x from 0 to infinity, but when I was numerically integrating to check the constant so that I could superimpose the PDF, I was getting some unstable behavior. And this was right before class, so I decided to save it by saying this is only for x between 0 and 6. In that case, if you integrate it, with by yourself or with Mathematica or something, you get a constant if you integrate this of like 0.3 something. And you can put a 1 over that 0.3 something in front of it to have the full PDF. Okay, so this is a very funny looking PDF, and I'll show it to you. I'll draw one. It's like, but these bumps are like leaning backwards. Okay, so because I had to change this to 0 to 6, I decided to make a candidate density. I decided to just use an exponential with rate 1. And I decided to use an independent candidate. So I'm just going to use a Q of y, and I'm going to let this be e to the minus y. But that's not on the right space. So I renormalize this, because if you just limit it to 0 to 6, then it's not going to integrate to 1. So you need to divide by the integral up to 6, right? And that's 1 minus e to the minus 6. That's the exponential CDF if you evaluate it at 6. So what we have now is something that looks exponential but is cut off. I can't believe you're still here. The internet's down and my neighbor's is down, and so I'm running off a hotspot on an 18-year-old phone. I don't know if it's going to hold, but thank you for staying. I'm really sorry about that. The recording is going. It's a good break time though, because I was about to switch to R. Okay, so let's go to R. Oh, yeah. So we had this wiggly PDF, and I decided to simulate from it using a truncated exponential. And you can actually write the CDF out and invert it for the truncated exponential. So here goes. What you're seeing is draws from the exponential distribution and the target. Oops. Here is, I'm blocking that. Here is one more time step. Wow, that's fast. Like that just got in line, like in one step. There's the next one, the next one, next one. I mean, that looks like it's done. It fits really well, and it did after maybe 2 time steps, which I was really kind of shocked by, but yeah. Okay, so that was exciting. I also, let me get to the end of this. I also decided to do it with a not as nice PDF. So here I'm using a uniform 06, and there's a histogram of my uniforms. That is 100,000 uniforms. Oh, by the way, this is, we're grabbing the end of a chain after, well, 1 time step, 2 time steps, 3 time steps here. And then I'm throwing everything out. If you have something that's really expensive to compute, you can go way out until you think it's converged, and then keep grabbing values because you're in that stationary mode. The problem is that if you want IID values, they are definitely not independent. So you can run one Metropolis Hastings chain for a long time and ignore it until it converges, and that's known as burn-in time. And then you can grab a value, and then you can grab like every 100th value from there or something to try to try to separate them. But this was fast enough that I just ran a whole new chain and grabbed the output. Okay, so let's go forward one time step. I left you at a cliffhanger. If it goes out again, let's just call it because there's not that much time left. But I left you with a cliffhanger. So we had the target density and we started with a uniform distribution. And after one step, it started having the 4 modes. So that's pretty nice. After 2 steps, it's, stretching up there. 3, 4. This one's slower than the exponential because it's a kind of bad starting distribution. You want it's just flat. So I obviously didn't mimic the shape with my exponential, but keep going. All right, it's looking pretty good around time 20. And yeah, so I was actually pretty surprised by that one as well. So I have more to say about choices and convergence, but that's the basic algorithm and how far I wanted to get through it today. And that is pretty cool, I think. I don't even know if this is worth it, but we're going back. We're going back to birth and death processes. So what I was going to do right now is to solve the differential equation that was given in your review problem, where I don't want to do this. It's not, I want to do something more fun with our remaining time. But we had like one of those machine problems where xt took on the values 1 and 0, and we wanted to find the transition probabilities at some time t, not just some time h. And we've never really done that except for the Poisson distribution. We know what that is. So I was going to solve Kolmogorov equations for you. I am going to put that on the end of the video that I post. You don't have to watch it, but let's just go forward because it's also in the solutions to review set 1. Okay, so that puts us in queuing. We're in queuing now. Queuing. It is the science of standing in line. Queuing. Yeah, and we saw 1 queue so far, and that was known as the MM1 queue. And those M's stand for memoryless, which means that you have exponential things, exponential inter-arrivals for customers and exponential service times. And the 1 stands for you having 1 server. So this, as you know already, means that you have a server and you have people coming in. They're actually coming in according to a Poisson process with rate lambda, and they're being served with an exponential amount of time with rate mu, and then they're leaving. So the inter-arrival times are, and this is just, why is it true? This is the assumption. When you say MM1Q, this is defined, are IID exponential with rate lambda, and the service times are IID exponential with rate mu. So we already know the stationary distribution. We did this as a birth and death process where lambda 0, lambda 1, etc. is supposed to be the birth rate when there's currently I customers in the system. By the way, I should say that that's what we're counting. So xt is the number of customers in the system, and not just in line, but in the entire system. So this includes the person being served at time t. And this is a birth and death process. We already did this stuff, so that's why I'm kind of blowing through it. The birth rate when there's currently I in the system is just always a constant lambda because the Poisson process is not looking ahead and not making any decisions here. The death rates are, well, when we have 0 in the population, then the death rate is 0. But mu I for I greater than 0, the death rate is then constant because there are no people racing to leave. If there's more than 1 person in the system, or at least 1 person, that person is in service, and the next departure is going to be after an exponential amount of time with rate mu. Yeah, so we used, I'm just going to write the formula and then I'll cut to the solution that we already know. But we used our favorite birth and death process stationary distribution formula. And we showed that the stationary distribution looks like 1 minus lambda over mu to the n for n equals 0, 1, 2 on up. And this is provided, so we need lambda to be less than mu, or the sum we had to compute to find pi 0 would not have converged. And that would just correspond to people coming in too fast for the server to keep up with them, and eventually the line blowing up to infinity. Okay, so something new I wanted to talk about. I'm not going to have much time left, but waiting time, the waiting time for a customer. This is the time until they get into service. If you want the time on average, if you want the time a customer spends in the system completely, it's known as a sojourn time, and I'll write that down next time. So I'm going to let W be the waiting time for a customer to get to the server or to get into service. This is a mixed random variable, mixed in the sense that it is discrete and continuous. It has a discrete component. Because the person could arrive and there's no one in the system. Their wait is going to be 0 if when they arrive, and I do mean for this to be in equilibrium, or this isn't going to make sense. I mean, we could actually do the problem, but it would be a different problem. So we are in the stationary mode. The probability of the waiting time is 0 is the probability that there are 0 customers when they arrive. And that is 1 minus lambda over mu. But that is also a dangerous statement to make, because the stationary distribution should be the same at all fixed time points, any point you want to come in and look, but not at these random time points that are determined by the customer process. So the question is, when a customer walks in, what they see in front of them, is that stationary? I know what they see behind them, if they step in and look over their shoulder, is not stationary or is not the right distribution, because there's always at least one customer in that system. And we know the stationary distribution here allows for 0 customers. So by actually taking the point of view of a moving customer, we might wreck stationarity. But we're going to show that an arriving customer, when they look ahead, what they see is the queue in its stationary mode. This is something known as the pasta property, which stands for Poisson arrivals, C time averages. And we're going to prove that. But also, we're going to finish this waiting time thing, because this is the probability the waiting time is 0. And then with probability lambda over mu, W has a PDF. And we're going to figure that out and put them together into like a mixture kind of density. And we're going to find their expected waiting time. And then we're going to see other interesting queues like MM infinity with an infinite number of servers. And I'll try to convince you why you care. Next time on Markov processes.
Ariel, listen to me. The human world, it's a mess. Life under the sea is better than anything they got up there. The seaweed is always greener in somebody else's lake. You dream about going up there, but that is a big mistake. Just look at the world around you, right here on the ocean floor. Such wonderful things around you. What more are you looking for?